All right, good morning, everyone. Let me start off by just want to point out some things from my website here. So we're on the AP Springs review page. Today we're going to be doing a little bit of finishing up from topic 5B, just these antiderivative topics on that second page. Homework for 5B is available, and today we're going to be going over quiz review worksheet 1. All right, and if we don't finish, we can finish this worksheet on Monday. I want to talk a little bit about tomorrow. Tomorrow is an asynchronous day, so attendance is not going to be taken. I'm not going to give any new assignments. It's just going to be a catch-up day for whatever you need to get done. But I do want to have some sessions available for going over, especially the homework worksheets. I haven't had a chance to really go over any of the homework problems off the homework worksheets. I made keys for it, but I haven't gone over any of it. So I'm hoping maybe tomorrow I could use that time to go over some of it. And then I'll also record these sessions. If you can't make these live sessions, you can always watch the recording. And these sessions will be held in the AP Calc Teams Help Sessions page or Help Sessions channel. So let me kind of go over what I'm going to do, and then you can join if you'd like. But again, this is all voluntary here. So 7:30, I'm going to start off by going over Chapter 7 worksheet for any students who want to have some additional support getting ready for the recovery test next Monday. So I have the team's recovery assignment on. I have that pushed out to you guys, and then if you are interested in wanting to do the recovery, you'll need to complete the assignment as well as do corrections on your test. If you are wanting to do recovery, I should have given back your test either through Teams or through Text Remind, so that you can do corrections on it. If you want to do corrections on your test but have not received your test back, let me know and I'll send that to you. 8:30, I'm going to go over homework worksheet 1. So basically that limits homework worksheet. But we can also use this all these times to answer any questions that you guys have. We can kind of have it, where we have an hour just devoted to limits. But if you don't have any questions, I'll just go over that homework worksheet 1 and I'll record it. 9:30, I'll go over derivatives and homework number 2. 10:30, I'll go over related rates, theorems, and homework number 3. 11:30, I'll do curve sketching and homework number 4. 1:30, I'll do the antiderivative FRQs and multiple choice. Homeworks 5 and 6, I may not be able to get to all the problems in both those homework, but I'll just pick off the ones that I feel maybe are the most challenging or the ones that you may want to see. 2:30, I'll do the FRQ and homework number 7. Basically, today's topic, I'll probably focus more on the homework number 7. If we don't get through with FRQ today, I'll save that for Monday to do in class. And 3:30, I'll go back to doing a help session for Chapter 7 for any students who couldn't make the 7:30 but want to attend the 3:30. Monday, we'll continue with a quiz review. Tuesday is asynchronous day, so no school, no classes, but your homework assignment is due. So your next batch of assignments 5 through 7, is due by Tuesday night through Teams. Wednesday, we'll do another day of quiz review, and then Thursday is your quiz. All right, any questions that you guys have about our schedule today and next week or Friday? All right, so let's go to our review sheet here. Let's finish that review sheet from yesterday, or at least do some parts of the second page. All right, we got through the first page of topic 5B, anti-differentiation multiple choice topics, and we did a little bit of the second page. We saw how these certain problems have a mixed depth integral involving function notation, and a lot of times we need to go through a cleanup stage using U substitution. U substitution allows us to get our expression to match a little more with what is given to us. And along the way, we also needed to convert the bounds so that everything in our integrand is in terms of the same variable. So if I go through U substitution, if I convert my integrand to be in terms of U, I also need to convert the bounds from X to be in terms of U. And then we use the conversion, the assigned expression between U and X to help us convert from one variable to the next. And once we're able to make that substitution, we're able to see a connection between what's given to us and what we're able to rewrite with our problem. And once we have that connection, we saw that we can substitute this expression or this integral with 15. And once we made that substitution, 15 divided by 3 is just equal to 5. A and C are similar in that sense, identifying the U value and working through that process. Don't have time to go over that today, but tomorrow I may be able to have during that time slot for this worksheet or for this homework, I can go through these two problems as well. But let's do the top of the page here. Average value theorem and first fundamental theorem application. So average value theorem takes on the form of f of c equals 1 over b minus a, integral from a to b of f of t. Now this is just a reworking of the area formula for a rectangle. Okay, anytime I'm thinking in terms of average value, visually what that means is I'm looking for the average height across all my graphs, right? So I can kind of imagine, okay, I have some points above, some points below. My average height looks to be somewhere around here, maybe somewhere around 2. Okay, but we're going to I want to kind of describe what this formula is saying. You know that area formula for a rectangle is just width times height. So imagine rearranging the equation to solve for height. If I want to solve for height, height is just equal to area divided by the width. And that's essentially what this formula is doing for us. We have the integral, which is area related, and then we're dividing by the width, which is that b minus a, right? If I subtract my a and b value, I get my width of these rectangles. So area divided by the width is equal to the height. So we're just, it looks complicated, but It's just a reworking of height formula of a rectangle. We have a graph of f of x that consists of a semicircle and 2 line segments. What is the average value of the graph on the interval from 0 to 8? So I'm just going to enter this into my formula here. My a and b values are given. That's 0 and 8. Insert into my theorem. One over b minus a, that's 1 over 8 minus 0. Definite integral from 0 to 8 of my function. Now, the nice thing is we have all these geometric shapes, so we can just total the values of these different areas that we see here. All right, so we see all this is above the x-axis, so we know this is all going to result in a positive value. We have semicircle here. We have a triangle here. And then we can think of this whole long bar as just a rectangle. All right. So f of c equals 1 over 8. And we're just going to go through and find the areas of each of these shapes here. So I have a semicircle. We know that's 1/2 pi r squared. We have a triangle. We know that's just 1/2 base times height. We have a rectangle. We know that's just width times height. All right, pi r squared, my radius is just 2. Okay, 1/2 pi 2 squared plus triangle next. 1/2 base times height. My base is 4, my height is 2. And then my rectangle here, width times height, 8 times 1. Do a little bit of cleanup here. I'll keep the 1/8 outside. Two squared is 4. 4 pi divided by 2 is just 2 pi. 1/2 and 2 cancels out. I'm just left with 4. And then plus 8, which is 12. So I can make that 2 pi plus 12 over 8. I can factor a 2 out. Reduce the 2 and 8 to be 1 and 4. Answer choice D. Any questions there? All right, number 6. This is a review of first fundamental theorem and its applications. So here's what first fundamental theorem tells us. We know the definite integral. It's basically just finding definite integrals, right? Definite integral from a to b of f of x dx. It's just equal to, we take the antiderivative of f, we make it turn into uppercase F to represent the antiderivative, and then we just take turns plugging our upper bound followed by lower bound. So f uppercase f of b minus uppercase f of a. Okay, so this is just the formula for problems that we've been working on that we know how to do. So just want to make sure we see that connection here. Really, if I ask you to find the integral of x squared from 1 to 2, this is basically applying the first theorem, right? So first fundamental theorem. So x squared is our original function. We find the antiderivative going through power rule, so we're able to transform our function to its antiderivative. So lowercase f turns into uppercase f, and then we take turns with the upper and lower bounds. Upper bound gets inserted first, so we plug 2 in. So this is my uppercase f, f of b, minus, then I plug in my lower bound, that's my uppercase f of a. Okay, so just want to kind of make sure that we understand this is just a formula form of something that we worked through quite a bit. First theorem can also be rearranged and applied in different formats, such as more particle motion problems, where I can think of it as any position that I'm looking for on the graph. I can think of it as a starting position plus however much distance I traveled in that between that time interval. And if I add those together, I can find out the location of my final position. So it's demonstrated here. Final position, x of b equals initial position, x of a, plus however much distance I gain between those two time values. So if I accumulate my velocity over that time period, that will tell me how much I traveled. And if I know the progress I made between those two time intervals, I add it to my starting point, I'm going to end up knowing where my final position is. So we can also take that concept and just apply it to different variations. I can say f of b equals f of a plus the integral of f prime, right? Just to kind of think of it as this is position, initial position, and displacement. Now we can also create these variations based off of these first theorems. So since this applies for position, we can also make it apply for velocity. Okay, just basically we're just taking these parts and just making it go one derivative down. So instead of final position, I can say final velocity is equal to initial velocity plus the accumulation of acceleration, which will give me the total velocity that I gained, plus my initial velocity equals final velocity. I can also apply that in this form here. Instead of f of b, I can say f prime of b is equal to f prime of a plus the accumulation of f double prime from a to b. Okay, so let's see if we can apply this method for this problem here. This is a common type of problem on multiple choice exams, so I want to make sure I go over it. It says if f is the antiderivative of this expression, such that f of 1 equals 2, then what is f of 3? Now, if the antiderivative of this expression will bring this expression up to f of x, then that tells me that this is really sitting at the derivative level, right? If I take the integral of a derivative, that's going to bring me up to f. So this statement is basically another way of saying I'm staring at the f prime function. Right, the antiderivative of my f prime will turn me into the f. Right, so that's what this is saying here. We have an initial position of f of 1, and we're looking for f of 3. So I'm just going to follow through with this formula here. I want to look for f of 3, so that's my f of b, that's my destination there. F of a is whatever is my starting point, whatever is given to me. So I want to know what happens between 1 and 3. So I'm going to accumulate that information between 1 and 3. So accumulate that rate. My f prime is this expression here. And we can just use our calculator to find that displacement. So f of 1 we know is 2. We enter this in our calculator here. And I got 0.397. So I started at position 2. I made a progress of 0.397. So I'm going to end up at 2.397. Okay, any questions there with number 6? All right, let's go to our review worksheet number 1. It says let f be a differentiable function. I think I meant for this to say f and f prime are differentiable. So both the f and the f prime function are smooth curves. Okay. The table gives values for f and its derivative as selected values of x. We have a g of x that's defined here. We have h of x that's defined. This slight adjustments here. These really should be different variables here. So I'm just going to use t for. Okay, this when it gets plugged in, it'll become x. But right now, I'll leave it as t. So it's the integral of my j function. Part A says, is there a value of c between 1 and 5 such that f double prime of c is equal to -3/4? Provide explanation for your answer. So we want to, the problem is saying, can we guarantee this particular second derivative value? And if we look at this, this should remind us of something that is maybe at the f prime level. What if the problem says, is there a value such that f prime of c is equal to -3/4? So if we're trying to guarantee a slope, we typically think in terms of, okay, that is trying, the problem is trying to guide us to apply mean value theorem, right? But this is just going to be an application of mean value theorem rather than guaranteeing an f prime. This problem is trying to guarantee an f double prime. So let me remind us what mean value theorem looks like. Mean value theorem says I can guarantee a slope, a particular slope on the curve, as long as the slope between the endpoints exhibits that value. Right, that's what mean value theorem is. But we can also adapt mean value theorem to represent something that is one derivative down. So I can say, well, I can guarantee f double prime of c if the slope of my derivative graph exhibits a certain value. All right, so I'm just transforming my f of x, just everything, just one derivative down. So that's how we're going to start our process here. If the slope between the endpoints of my derivative graph gives me -3/4, then there must be a second derivative. There must be a slope on the derivative graph that also matches -3/4. So our a and b values are provided. That's 1 and 5. And I'm just going to take the time to replace the a and b with these specific values. So f prime of 5 minus f prime of 1 . Okay, so all I'm doing is I'm taking my adapted version of mean value theorem, and I'm just going to see if this value gives me -3/4. If that gives me -3/4, I can guarantee that there must be an f double prime that's equal to -3/4. So look at my table of values here. F prime of 5 is -2. F prime of 1 is 1. So I'm going to start entering values that I find. So f prime of 5 is -2. F prime of 1 is 1. That gives me -3/4, so we can guarantee it, yes. The slope between the endpoints of my derivative graph is -3/4, so that means there must be a slope on my derivative graph that is also exactly -3/4. Right. Provide an explanation. Then there is a point on the interval where f double prime is equal to -3/4. Okay, so just to give you, as a reminder, a visual representation of mean value theorem, imagine if this curve was not f of x, but f prime, right? And we found the slope between endpoints of my f prime graph to be -3/4. So if the average slope of my f prime is -3/4, then there must be a point on my f prime graph where the slope of my f prime is also equal to -3/4. And a way of saying the slope of f prime is calling it f double prime. Right. If this slope is -3/4, there must be a slope on the f prime graph that is exactly -3/4. So we're taking mean value theorem. We're just kind of pushing everything down another derivative. But same idea. Any questions with A? All right, part B. Let K be the function defined by K of x equals f of j of x. Write an equation for the tangent line to the graph of K at x equals 2. So if I want to find the equation of the tangent line, I to gather some information, right? I need to identify order pair, and I need to identify slope. So I have some information about order pair. I know the x value is 2, but I still need to figure out what that y value is. And then I also need the slope, which I'm going to find using the derivative. All right, first things first, let's find the ordered pair. Ordered pair is going to come from our defined function here. So if I want to find my ordered pair, I'll just replace 2 in for x and see what that can give me. So k of 2 is equal to f of j of 2. And j of 2, let's see, what is that going to give us j of 2. There's my j graph. J of 2 is just my ordered pair. So j of 2 is sitting here at -1. So I'm going to update this here. Replace j of 2 with -1. Okay, so I just made that replacement inside my bracket. And now I'm down to f of -1. So f of -1, let's see, that's in our table, right? F of -1 is just equal to 4. So there are a series of figuring out our composite function here. We have our ordered pair figured out, 2, 4. Next up, we need to find the slope. To find the slope, we need to find the derivative. To find the derivative, we need to recognize this as a function within a function. So we need to go through chain rule. Okay. So let me remind us of our chain rule here. Chain rule says if I want to find the derivative of something, of a function within a function, something that is in composition form, I need to take the derivative of the outside portion and multiply by the derivative of the inside function. Let's see if we can apply that for our specific function defined to us. So if I want to find k prime of x, because I have a function within a function, I'm going to go through chain rule. I'm going to take care of my outer function first. So f is my outer function, so it's f prime of j of x. Times my inside function's derivative. My inside function is j, so therefore the derivative of j is just going to be j prime. Now that we have our derivative spelled out, I can evaluate my derivative at 2. All right, let's evaluate this one piece at a time. This is a complex expression here, but let's take care of it one piece at a time here. So j of 2, we go to our j graph here. J graph is just going to be at -1. Make that substitution. So we're down to f prime of -1 times j prime of 2. Okay, so f prime of -1, we go to our table. F prime of -1 is -3. That's the first part. And then j prime of 2, this is our j graph. We want to find the derivative, or in other words, the slope of the j graph at 2. We see that at 2 is part of this line segment. So if I find the slope of this line segment, I know the slope of my j prime at 2. So I'm just going to pick 2 points here. This is obviously a negative slope. So I'll do rise over run, down 2 over 1. That's the slope of -2, right? Down 2 over 1. So from the f prime, from the table, I can identify f prime of -1. And then from the graph, we just look at the slope of that line segment, which is -2. And now we're down to 2 numbers that we can combine to find k prime of 2. All right, we have our slope. Now we can work towards our point slope form, our tangent line equation. All right, any questions with part B? All right, we're practicing chain rule there, applying chain rule, and being able to use table of values to piece by piece get from these function notations into a numeric value. All right, part C. Find the slope of the tangent line to the graph of g at x equals pi. So to find the slope of the tangent line, I need to find the derivative. From the derivative, I can then plug in pi into the derivative to find the slope. So we're talking about the graph of g here. So let's see what is defined for us for g. G of x is defined as sine of 3x minus e to the cosine of 2x. So I'm going to write that here and see if we can find the derivative of that function. So if I want to find g prime, a couple things I need to apply. I need to involve sine's derivative. I need to involve e's derivative, and I also need to involve cosine's derivative. So let me write those rules here. So sine of u is just cosine of u times u prime. E to the u's derivative is just e to the u times u prime. And then cosine's derivative is just negative sine of u times u prime. All right, let's see if we can apply them accordingly for our function here. So let's start with the first term. All right, sine of 3x, we're going to follow the rule here. So sine of 3x is just cosine of 3x times 3. Next term is e to the u. So the rule for e to the u is e to the u. So e to the u is going to show up in our derivative. So I'm going to write that down first. No changes. It's all going to be recopied over. So e to the u times u prime. So u prime is referring to the entire exponent's derivative. So the entire exponent is cosine 2x. So I need to find the derivative of that entire cosine 2x. And the derivative rule for cosine of u is negative sine of u times u prime. So in this space here, I got to find the entire cosine's derivative, which will be negative sine of 2x times 2. So we're just inserting the exponent's derivative here in this space. I'll do a little bit of cleanup, and then we can evaluate the derivative at pi. I'll push the 3 out in front here. All this is one term, so I'm going to combine the two negatives to be positive, and I'll push the 2 out in front. Okay, I'm ready to enter in my x value of pi. All right, let's see what that cleans up to be here. Cosine of 3 pi is just same thing as cosine of pi, which is -1. E to the cosine of 2 pi. Cosine of 2 pi is just 1. E to the first power is just e. So 2e. And the sine of 2 pi is just 0. So 2e times 0. And we know anything times 0 is just going to be 0, so that's going to go away. So g prime of pi is just -3. The problem is only asking for the slope, so that's all we need to provide. Not the tangent line, we just want to find the slope. Okay, questions there? All right, part D, find h of 4 and h prime of 4. All right, let's see what is defined for us. H of x is defined as the integral from 6 to x of j of t dt. I'll copy that down here so we can just reference it. If I want to find h of 4, I simply can just replace x with 4 and see what we can do from there. So our j graph is here. We want to find the definite integral of the j graph from 4 to 6. So we know it's just going to be adding up area of our geometric shape. So, but the thing is, we typically like to read the graph from left to right. And to make it easier to read, I'm going to adjust the bounds or flip the bounds so that I can go from 4 to 6 instead of from 6 to 4. It just feels like we have more things to keep track of if we have to kind of think backwards in our heads. So I'm going to rewrite the problem to make it easier to think about. So I want to go from 4 to 6, but because I'm adjusting the bounds, I need to push a negative in front. So the region from 4 to 6 of my j graph is just going to be this triangle here. And we know the area of a triangle is just 1/2 base times height. Base is 2, height is 3. The 2's cancel out. I'm just left with 3. So h of 4 So I just rewrote that triangle formula value that we have there. So 2's canceled out, which is left with 3, and so h of 4 is just -3. Okay, so we have that part figured out. Next part, we want to find h prime of 4, but to find h prime of 4, let's first figure out what h prime of x is before we decide what to do, before we plug in. Okay, so if h of x is defined as the integral from 6 to x, then h prime must be the derivative of this expression. So h prime is just, I'm going to write this out here, derivative of my expression. And whenever we see this, hopefully we're able to just think of this as, oh, this is second theorem here. This is basically just allowing us to cancel these operations out, right? I'm applying the integral and I'm turning around and applying the derivative of that integral. So anytime I see these two operations paired on top of the same function, I know that they're just going to go, they're going to take each other out, and the only thing left is going to be the j, but the upper bound is going to be entered into the variable. So it's going to be j of x times 1, and that, well, times 1 because x's derivative is 1, but it's not going to have any impact. So my h prime is just going to be left with just that j of x. All right, so h prime equals j of x. I want to find h prime of 4. So if I want to find h prime of 4, then I just need to find j of 4. And j of 4 is just asking for the ordered pair, the y value of the j graph at 4, and the y value is just 0. So h prime 4 must be just 0. Any questions there? Okay, let's do one more here. Let's go to the back, and I want us to do part E. So part E says, on what interval is h increasing and concave down? Right. So we know h is defined as the integral from 6 to x of j of x. So we know there's some relationship here. Okay. So as a reminder, just like similar to what we did with part D, if h of x is the integral from 6 to x of j of x, then again, that is a reminder that j is really sitting at the h prime level, right? And just like how we did with part D, we knew that derivative and integral will cancel each other out. So anytime we see this expression, we know that, okay, this means that the j is really an h prime graph. This is, we're looking at the h prime information here. So just as a reminder, we're staring at the h prime graph. Okay, because we've established that relationship. Now, if I want to find when the h graph is increasing and concave down, looking at the derivative graph, then let's switch gears, right? We know how to read the derivative graph, and so that's what we're going to apply here. Anytime I'm looking at the derivative graph, I want to kind of give myself reminders by labeling what I'm looking at here. So I know anything above the x-axis of my derivative graph is going to demonstrate to me where my original graph is going to be rising. Whatever is below the x-axis of my derivative graph is going to indicate where my original graph is going to be falling. So I will create an h prime sign line. I'm looking at the interval between 0 and 6. And to find my critical point, I need to identify my x-intercepts, right? X-intercepts will be where my critical points is, where my slope is 0. So looks like that's between 1 and 2, so I will call that 1.5. So 1.5 and 4. We know that between 0 and 1.5, that is going to be a positive in the positive slope region. Between 1.5 and 4, that's going to sit in the negative region. And then between 4 and 6, it's sitting in the positive region. I also want to, so this will give me information about increasing, decreasing, right? So that information is going to be helpful. Concavity, we can also pull information about concavity of the original graph from the derivative graph by picking out critical points. But the way we find critical points from concavity's perspective is we look at the peaks and valleys, right? We're trying to target and find those points of inflection. So points of inflection is going to live peaks and valleys of our H prime graph. So we have max at 1, so there's a point of inflection at 1, point of inflection at 3, and point of inflection at 5. I'm trying to line up so it'll be easier for us to identify. Between 0 and 1, we can see that our slope is positive. So positive slope on the F prime graph is going to correspond with concave up. Between 1 and 3, negative slope is going to correspond to concave down. Between 3 and 5, positive slope is going to correspond with concave up. And then between 5 and 6, negative slope corresponds with concave down. So let's see, can we find the intervals where our graph is both increasing and concave down? So I'm looking for up arrow and I'm looking for concave down. So I see a pairing here between 1 and 1.5, right? We see that this interval, both properties are shared at the same time. And another place where our graph is increasing and concave down between 5 and 6. All right, so we can state that. All right, any questions there? We didn't get to F and F and G, so we will do these on Monday. Okay, I'll finish this on Monday. But tomorrow, if any of those help sessions sound good to you, feel free to join in the help sessions channel. But again, not required. Tomorrow is just a day for you to catch up with anything you need to do with this class or with other classes. But as a reminder, Monday is the recovery test for Chapter 7. Let me know today if you want to take that recovery test and complete those assignments. But if I don't see you tomorrow, I'll see you guys Monday. So have a great weekend.